next presentation will be made by Felipe Diniz. He worked for Petrobras for 11 years. He is engineer, design, automation consultant, and he's an electronic and computer engineer and has master's degree and PhD degree in signal processing. And he took part of a team who worked in fields of 58, 62, 600,000 and software frequency. Felipe, please.
Good morning. Our work philosophy is to take data, turn it into information, and then turn it into knowledge, and finally into wisdom. This is the role played by integration between engineering, design, automation, and constructability. But what is constructability anyway? Well, constructability is the integration and application of construction expertise throughout all product phases. And it comes as a benefit for cost, schedule, quality, and overall goals. And constructability is the main actor in quality assurance program for Petrobras pre-salt replicants projects. The design of all new units is fully reviewed for constructability throughout detailed engineering, using lessons learned, and items are evaluated based on team past experience from previous projects, and it's all fed back into the design. Okay, in Petrobras, quality strategy, both lessons learned and constructability have their own dedicated workshops. On those workshops, all items related to each discipline are identified and evaluated. And all problems ranked with high risk, high potential risk, for future projects have to be presented with possible solutions. And they have to be inserted in the action plans and regular follow-up activities. But as I told you, it all has to go back to the design. But how can I accomplish this? I mean, how can I take data and turn it into wisdom for these issues never happen again? The answer is by using engineering design automation. Our team's job is to take issues that are considered to be harmful to the engineering design quality, compile them into lessons learned and engineering rules, and implement computer programs that will be able to make automatic analysis for some questions raised by these lessons learned and engineering rules. But what is engineering design automation anyway? I'd like to explain it by telling how engineering design was elaborated throughout history. And in the beginning there was paper all around. And the problem with paper is that paper accepts all your mistakes. It doesn't complain about them, and it sweeps them all under your rug. Actually, paper sends those mistakes to a black hole where no one can find them until it's too late. With the computer era, CAD came along, and CAD is computer-aided design. But CAD doesn't solve your problem. It only makes the computer help you to make the same mistakes from before. Only with computer-aided engineering, or CAE, the computer systems actually reach its own full potential for engineering design. And with this kind of approach, there is a computer system that is capable of criticizing your work. And is capable of doing this because it views the elements of your documents and drawings and schematics and models as elements that belong to a well-structured database. And for this database, each component has its own meaning. And that's where its power comes from. But how can a database can represent engineering design? Here is a small and very simplified example which can illustrate it. Consider this small design, and this is the database which can represent it. And you can think of a database as a set of related tables. So when you every element of this engineering design has its own counterpart in this database. So equipment has its own table. Pipeline has its own tables. And every register in those tables represents an element from this engineering design. But there's more to it. There is also another table which represents which elements are connected. And following the instructions represented in the database, you can easily recreate this engineering design. And you can see that this database has a full correspondence for this engineering design. But the true gain here is this kind of approach can allow you to generate automatically equipment lists, pipe lists, extract to-from information, and make automatic consistency analysis. For instance, you can check if processed information from connected items are actually consistent. So with this mindset, I'll show you 3 analyses that were results from constructability workshops related to instrumentation. The first analysis is verification for impulse line position for pressure and flow instruments according to API RP 551, which is process measurement instrumentation. The goal here is to verify if the instrument hookup position presents self-draining characteristics for gas and self-venting characteristics for liquid. Those cases are summarized on this figure. For instance, if an instrument deals with gas, it has to be mounted on the upper quadrant of the pipeline. Why is this? Because if there is any liquid present on it, this liquid would be naturally drained back to the pipeline. Okay? In order to do this verification, there is a 3-step procedure that was automated by engineering design automation. So the first step is to make a list of all pipe runs contained in the pipe PNID database along with their fluid state. So it has to indicate if this pipe run carries liquids or gas. The second step is a twofold one. The first part is to make a preparation for criticality analysis, and based on our company's knowledge base, we have to classify every system present in this project as more critical or less critical. And the second part of this twofold step is to make a list of all 3D model instruments along with those informations here. Okay? And line orientation, instrument orientation, it's all reference to this figure, where the quadrants and horizontal and upper quadrant, lower quadrant, they are all represented here. Once you did it, you can move on to the classification itself. And the classification, basically you have to pick one of those patterns to the hookup position configuration. For instance, if none of those, if one of those patterns fits, then it's okay. If none of those patterns are proper to this configuration, then this instrument has to be verified. For instance, let's look at this second line. If the line orientation is horizontal, the fluid state is gas, and the instrument orientation is horizontal, then the system will suggest, look, this instrument orientation needs to be upper quadrant, and so on. Okay? The second analysis is flange material in process connection. So for all pipe run mounted instruments, we need to see if the material, the flange material has the similar material that may cause galvanic conversion. Okay, and this is accomplished also with a 3-step procedure. The first step is to list all pipe run mounted instruments. And an instrument is considered to be pipe run mounted if it presents one of these configurations: pipe run and process connection and instrument, or pipe run, secondary pipe run with piping valve and instrument, or a pipe run with the inline instruments. The second step is to list all 3D model instruments that are connected to a piping component through a joint. And the third step is to join those two results in order to compare them to the component's knowledge base, and then identify if there is any chance of the similar material for the flange in the process connection. The third and last analysis to be presented here is about straight pipe length in flow meter configuration. Some pipes that belong to the flow meter arrangement have to present minimal length. So, in the end of this analysis, we have to come up with this table containing the flow meter tag, its location, and the length of all these pipes: the downstream pipe length, the distance between profiler and flow meter, the upstream pipe length, and the distance between the flow meter and the temperature meter. And it's all normalized by the pipe inside diameter, and it all has to be according to ISO 5167. And how do we accomplish this? With one more time, a 3-step procedure that was automated. The first step is to list for all flow meters in 3D model database the flanges that belong to this arrangement. The flanges here will act as the limits for all pipes whose length needs to be calculated. Then we have to estimate if those flanges that belong to each flow meter arrangements are upstream to the flow meter or downstream from it. And then, at the end of this analysis, we have to calculate this is based on the interface defined by the flanges. and we have identified those flanges based on its index and orientation. And in conclusions, we have demonstrated that automated verification of engineering rules are very useful, and they bring advantage in both time and effort in the long run. The main goals of each analysis were successfully achieved, and with minor adjustments, they can all be reused by other projects in the future. Other queries and analysis are being developed for other disciplines, since this whole approach of using engineering design automation has been proved to be successful. And constructability value improving practice, or VIPs, combined with engineering design automation, were demonstrated to be key factors for detecting and preventing inconsistencies in all these projects. And considering the amount of documents and interfaces and schematics and models and their size for this recently elaborated mega projects, those approaches were demonstrated to save time and resources when compared to conventional methods. And that's it. If you have any questions, I'll be happy to answer them.
Thank you, Felipe. We have about 7 minutes for questions.
I'm having trouble hearing you.
Speak loud. Congratulations on your work.
Thank you.
It's very interesting. I'm Felipe from UAE. And this system is open for other sectors of Petrobras or only for profit? Because today, when we need to look at analysis, I use Silverback. And Silverback is terrible. And when I need a 3D drawing, I don't have the drawing of recent spot forms. And it's powerful tool for my job. It's open for other workers or only for our sector.
So the question is if this kind of tool is available for anyone else besides Petrobras.
Yes.
Depends on the analysis. We have a big system which contains most of our analysis, and this system is only available for Petrobras. But some of our analysis, and I think those 3 I included are simple queries into the database. So if, we can make them available for other players.
Okay, thank you.
Thank you.
More questions? Felipe, I'd like to know if this tool can be used to the other disciplines, and maybe then can be used to help the operational
Okay. Did you hear the question? Can I repeat? Or repeat. He asked if there is any other disciplines to be involved on this kind of verification. So we are already working on some other disciplines, such as ergonomy and process and piping. safety arrangements. For instance, for ergonomy, we have analysis about valve height. For process and piping, we have what we call energy tracking, which we can map all incomes and outcomes for all project piping, and we can compare them to the 3D model. If all pipes that will be actually constructed have been designed in the same way in PNMT. So we have a lot of other disciplines involved. And the other question is about operation. This whole approach can be used on operation life, the whole life cycle of the plant.
Okay, we are on time. I'd like to thank you for
Thank you.